So let's keep up with finding the interval and radius of convergence. Let's hope they're not all as long as the last one, which took us 2 pages. So number 1, let's do the ratio test. Notice there's a factorial in this problem, so of course I'm going to use the ratio test. What else would I do? So I'm going to take the limit as n goes to infinity of, and I'm going to kind of cut out the middleman here. It's going to be a sub n plus 1 divided by a sub n, right? So it's n plus 1 factorial times 2x plus 1 to the n plus 1 over n factorial times 2x plus 1 to the n. And in order for this to converge, this must be less than 1. Sorry, I just realized as I wrote that, this is one time, and it's not very often, where I actually want to write it like that, just to kind of remind myself. Okay, so let's think here. N factorial and n plus 1 factorial. So n plus 1 factorial is n plus 1 times n times so on. So n factorial will cancel and leave you just n plus 1. Let me show that just a little bit. So that's the limit as n goes to infinity. You technically don't have to show this step, but I just want people to see factorial isn't something we do a lot with. Well, it's something we're doing a lot with now, but it's not something we did a lot with before. And then n factorial is n times n minus 1, and so on until 3, 2, and 1. And then I'll just leave it 2x plus 1 to the n plus 1 over 2x plus 1 to the n, although we all know what's going to happen there. And that must be less than 1. And again, normally you don't need to show this step. I'm just doing this because these are notes and I want to remind everybody how this works. So these all cancels, and the only thing you're left with is an n plus 1. So you're taking the limit as n goes to infinity of the absolute value of n plus 1 times, and then over here, 2x plus 1, 2x plus 1 to the n plus 1. So this is all gone and leaves you a 2x plus 1. Now 2x plus 1 does not actually enter into this at all. There's no n in there. So I can take the absolute value of 2x plus 1 out of the equation, or out of the limit I should say. And then I'm having the limit as n goes to infinity of the absolute value of n plus 1. And if you're thinking that's a problem, you would be right, because the absolute value of n plus 1 as n goes to infinity is infinity, right? So this is a problem. That's infinity. So how in the world, if I take something infinitely large, how can I make it so that it's less than 1? So if this is 1,000,000, how can I make this less than 1? And the answer is there's only one way, and that is if this portion over here is equal to 0. Because if this was equal to 0, then 0 times 1,000,000 would be 0, right? 0 times 100 would be 0. So this would work, right? So the only way this is possible, the only way I'm going to be less than 1 is if the absolute value of 2x plus 1 is equal to 0. That's the only way. Because 0 times anything, then this would work, right? So, 2x plus 1. My 1 turned into a, here, 2x plus 1. There it is. My 1 turned into my absolute value sign. All right, so 2x plus 1 is equal to 0. And then, of course, I would need this to be positive. Well, it wouldn't, the absolute value then is no longer relevant, because if it's equal to 0, then there is no absolute value. So that would mean 2x plus 1 equals 0. That means 2x equals -1. That means x equals -1/2. So that is my interval of convergence right there. It's a specific value. Which means I am in case 3 of Theorem 11.3. So if you look back to Theorem 11.3, the one that has a specific value is case 3. It only converges at, in our case, x equals -1/2. So this is Theorem 11.3, case 3. And the radius, of course, is 0. Because it's only converging at one value. That value does not have a radius. It's not really an interval. I mean, we call it an interval, but it's not. So the radius of convergence is equal to 0. And while I'm on the subject, they didn't ask, but the interval of convergence is the center. So it would be interesting to note this value is the center, which is the interval. That's all there is, right? The center is the interval. So we've seen a case 2 example, and we've seen a case 3 example. Any odds on the next one being a case 1? Let's see if it works out. Okay, so this is actually one I'm not going to do the ratio test for, wonder of wonders, because I noticed there's a tower function in there. And a tower function is a time to use the root test. The root test is quite useful for tower functions, in fact. Let me remind everybody really quick. If you remember back to our guidelines in chapter 10, if you have a tower function, right, some subscript of the n to the n, or some subscript of k to the k, you want to use the root test. So actually, on this particular problem, I'm going to use the root test. We'll make a note, though, of why we're using it. So, note. Tower functions n to the n in the denominator, so use root test. As opposed to the last one, which had a factorial. Factorials is a red flag to use the ratio test. But in this case, we're going to use the root test. Okay, so let's use the root test. The root test says that rho is equal to the limit. My rho is terrible, sorry about that. Rho is equal to the limit as n goes to infinity of the nth root of the absolute value of x minus 6 over n to the n. Just real quickly, let me remind everybody, if you have x minus n to the n and n to the n, right, you can make it x minus 6 over n to the n, just like I did here, right? Especially since there's an absolute value involved. All right, so then this is the limit. Oh, and of course, just like the ratio test, we need this to be less than 1, right? So this is the limit as n goes to infinity of, and the nth root and the n power undo each other. So I'm left with x minus 6 over n. Okay, so the x minus 6 doesn't really have anything to do in there. So I'm going to take that out, just like I've done before. Right? There's no n in it, so it's just going to come out. And that leaves me the limit as n goes to infinity of 1 over n. But this part right here is 0, right? We know that the limit of as n goes to infinity of 1 over n is 0. So that means that I have the absolute value of x minus 6 times 0. When is that less than 1? That's your rho value, right? For what values of x will that be less than 1? Well, for all values, because whatever this is, whatever it is times 0 will be less than 1, right? It could be 7, could be 17, could be 70 million, doesn't matter, right? It's always going to be less than 1. So, but that means rho is equal to 0, which is always less than 1. Here, maybe it'll be clear if I just get rid of that part. So you have the x minus 6 times 0, that's 0. 0 is always less than 1 for all x. Therefore, my interval of convergence would be negative infinity to infinity. My radius of convergence would be infinity. If you want to think of it having a center, centers can be defined by the formula. So technically its center is 6 because it's x minus 6. However, it's kind of irrelevant as far as the radius and interval of convergence part is concerned because there is no center to negative infinity to infinity. So the whole idea of a center doesn't really make any sense for interval of convergence when an interval of convergence is infinity to negative infinity to infinity. I mean, if you want to think of it as 6, then that's fine, but it's not going to hurt you. All right, so then this would be, of course, Theorem 11.3, case 1. We've seen all 3 cases. This one is the case where, right, the interval of convergence is negative infinity to infinity, and the radius of convergence is infinity. So in summary, there are 3 different types, and you use the ratio test and the root test to define them. Those are the 2 big ones. Ratio test, quite frankly, is used more often, but the root test is very useful for when you have a tower function. So this particular one, you use with a tower, like n to the n. This one you use with n factorial. If there's factorials anywhere, you use ratio test. And then the rest would be up in the air. Honestly, we use ratio test 90% of the time. Okay, so we use that to find the interval of convergence, where it converges absolutely. The radius for the interval of convergence depends. So your radius is infinity if your interval of convergence is negative infinity to infinity. That's what we just saw in this example. If your radius is 0, then you have only convergence at your center, which is x equals a, which happened in the last problem. And then if you have, last problem, I was going to show it to you. This one. Your radius of convergence is 0, so then you have a specific value. And the other option is that you have an interval of convergence and it has a center and a radius, which will be the 3rd case here. Right? So you had a minus r, a plus r. You take your center minus your center plus radius, and you have endpoints. But determining whether the series converges at the endpoints requires analyzing the series. In other words, here, down here, it's talking about determining, in other words, it's saying, check your endpoints, which of course is what made that other problem last for 2 pages. We had the interval and the radius pretty quick, but we had to check the endpoints, which required a whole other level of work.